Let's take a look at another example of a block sliding down an inclined plane. This time we will not be solving for the acceleration, and so I'm giving you this type of an example so that you don't fall into this pattern of memorizing the steps of how to find the acceleration. It's important that you understand the concepts involved when something is on an inclined plane, meaning you have to break the weight into horizontal and vertical components, or components horizontal and vertical to the plane, and how those affect its motion. So here's a plane, and we don't know how sticky it is. We don't know the coefficient of friction. We know the acceleration, we know the angle, the steepness of the plane, we know the mass of the block, and to be honest, we actually don't need to know that, just as Galileo proved with the big bowling ball and the small bowling ball or cannonballs or whatever they were. They fell at the same rate, and the same would be true here. But here we go. So, when we draw it out, create our triangle, our first step is to, we know the block has a mass of 2 kilograms, so we know the weight from W equals mg will be 19.8 newtons, assuming we're on Earth. This isn't really drawn to scale. That looks a lot more than 20 degrees, but here's our 20-degree angle, our right triangle, and our component of the weight parallel to the plane ends up being 6.77 newtons using SOHCAHTOA, and our component of the weight perpendicular to the plane will be 18.61 newtons using SOHCAHTOA. So again, this perpendicular component of the weight is going to exactly cancel out with the normal force. We know this is true because the block does not experience an acceleration up or down. As it slides down the plane, it's not moving up relative to the plane. It's obviously not moving through the plane. Okay? So the fact that the block moves in this direction indicates that this component of motion and this component of motion exactly cancel each other out. For the components of force that are parallel to the plane, so the weight pulls downward, friction pulls upward, those will probably not be equal, and the block will move. So it turns out that this block is moving downward. It has an acceleration of 1 meter per second squared, so we know that the force upward due to friction is less than the force downward due to weight, but we don't exactly know how much. So we will solve that in the next step. So a true free body diagram. Down the plane, we have a force of, I'm referring to my notes since I can't see those numbers anymore, 6.77 newtons, it looks like. Yeah. And up and down relative to the plane, the component of force was 18.61 newtons and 18.61 newtons. Okay, so this force we would call the component of weight perpendicular to the plane. This force we would call the normal force. It is the force that the plane exerts on the block. Okay, this is the force we look at when we go to calculate the actual frictional force. Okay, so friction's back here, and we know that it is the coefficient of friction times the normal force, 18.61. So the actual net force on the block is going to be the force down the plane minus the force up the plane. Okay? And net force, you know, is F in F equals ma. I'm going to write that because it is important. Net force. Always? Yes, always. So, given that we know the mass and the acceleration, net force, I like multiplying those numbers, 2 newtons, okay, and we know that is the difference between this, the force down the plane, and the force up the plane. We know that it's moving down the plane, so we know this force is more than this force. So we can say force down the plane minus the force up the plane equals the net force. Force down the plane minus the force up the plane, oops, I'm running out of space, equals the net force. And if we solve by subtracting first, I don't have to do the basic algebra with you, but it looks like this. Oops, there's a minus sign there. This should be erased. Good, the eraser tool works. Mu and 18.61. Yielding a coefficient of friction of 1.26. Notice how the coefficient of friction is a unitless quantity because it's simply a ratio of two forces, the force of friction and the normal force, the stickiness between two surfaces, and this all looks good.